everyone! Today we're tracing the fascinating life cycle of data. We're going to go on a journey from the very conception of a program's logic, down into the strict, rigid rules of C programming, and then all the way over to the quirky and, honestly, sometimes deceptive world of modern JavaScript. So let's unpack exactly how data is born, stored, and ultimately truly protected in this explainer.
Here's our roadmap for today's explainer. First, planning your program's logic. Second, storing data in memory. Third, the power of constants. Fourth, the JavaScript const illusion. And finally, achieving true immutability.
All right, let's kick things off with Section 1, planning your program's logic.
Okay, so a lot of people think computer science is just, sitting down and furiously typing code like you see in the movies. But the reality, it's quite different. The 6 fundamental steps of problem solving actually start with defining the problem, then planning, designing, coding, testing, and finally maintaining. Did you catch that? Coding is all the way down at step 4. Rigorous planning and designing literally have to happen before a single line of code is ever written. Without a solid visual blueprint, you're basically just building a house of cards.
And right here is a brilliant illustration of that visual blueprint. What we've got is a standard flowchart, a graphical algorithm designed to input 2 numbers and figure out which one is the largest. Notice the specific shapes being used. Those start and stop ovals, they mark the absolute beginning and end of our algorithm. The parallelograms are where data enters and leaves our program, so inputting num1 and num2 and then displaying the result. But the real magic happens in that diamond shape. That's a decision symbol. It asks a simple true or false question. Is num1 greater than num2? Depending on the answer, the flow of control branches off. It's just a perfect visual representation of our logic.
Moving right along to Section 2, storing data in memory. The absolutely crucial concept here is the variable. By definition, it's a named memory location used to store data of different types that can be retrieved and modified. To make this concrete, just picture physical, labeled storage boxes sitting right there inside your computer's RAM. When you declare a variable in C, you are essentially claiming an empty box in memory, scribbling a label on the outside of it, and stuffing your data inside. Whenever you need that data later, maybe to do some math or print out a result, you just ask the computer to go look for the label on that specific box. But here's the catch. You can't just scribble anything on those boxes. Looking at the naming rules, valid identifiers have some really strict constraints. You can use letters, digits, and underscores, something like _Rujan or Srujan812. But check out the invalid ones. You absolutely cannot have spaces. Something like Srujan space Pujari will completely break your code. You can't start with a number, and you certainly can't use reserved C keywords like goto, for, or switch. And on top of that, we have data types. This dictates exactly what shape of item can actually fit inside the box. Is it a primary type, like an integer or character, or maybe a derived type, like an array? Both the label on the outside and the box's shape must be perfectly defined.
Now for Section 3, the power of constants. So how do we lock things down? Look at how we declare constants in C. We simply add the keyword const right in front of the data type. But here is the rigid, unforgiving rule of C. You must initialize the constant variable at the exact moment of declaration. Notice the red X's there. If you just write const int var semicolon and then try to assign it a value of 5 on the very next line, the compiler is going to throw an error. No way around it. You have to do it all at once. Const int var equals 5. Think of a constant as a heavy-duty locked safe. The exact moment you build that safe, you have to put your valuables inside and lock the door permanently. You cannot build the safe, leave the door wide open, and just come back later. It's also vital that we draw a clear distinction between constants and literals because they are entirely different entities in C. Let's break this down really simply. A constant is the locked safe itself. It's a read-only variable that has an actual physical address in your computer's memory. A literal, on the other hand, is the raw fixed value you put inside the safe. The literal is the actual number 24, or the character A. The constant is the container, the literal is the content. Make sense?
Which brings us to the twist in our story. Section 4, the JavaScript const illusion.
All right, so here is a $1 million question for all my web developers watching. Does the const keyword in JavaScript actually freeze your data? If you're coming from the strict, deeply protected world of C we just talked about, you'd probably assume the answer is a resounding yes. But prepare to be surprised.
Here is the grand illusion of JavaScript's const keyword. Yes, it's block scoped, and yes, it absolutely prevents variable reassignment.
If you declare a variable with const user equals an object with name John, you cannot later say user equals an object with name Jane. It actively stops you from assigning a totally new object to that variable name. But, and this is a massive, massive but, it completely allows mutation of the object's internal properties. You can absolutely write user.name equals Jane and JavaScript will happily allow it. You haven't locked the safe at all, you've just superglued the safe to the floor, so it can't be moved, but the door is still wide open for literally anyone to reach in and change the contents. So how do we fix this? Let's dive into Section 5, Achieving True Immutability.
The hero of this story is object.freeze. Let's compare these two concepts directly. While const only prevents you from reassigning the variable identifier, object.freeze actually targets the object itself. When you pass an object into object.freeze, it returns a truly immutable version. No new properties can be added, none can be removed, and existing properties simply cannot be changed. If const is gluing the cardboard box to the floor, object.freeze is taking that entire box and freezing it inside a massive block of solid ice. The contents are completely suspended and protected.
But wait, there is one final caveat you absolutely need to know. Object.freeze is shallow. What does that mean? Well, if you have an object nested inside another object, that inner object is not frozen. It remains completely vulnerable to mutation. To achieve total immutability for deeply nested data, developers have to write custom recursive freezing functions or rely on specialized external libraries like DeepFreeze or Immutable.js. The ice only covers the outer layer, so you have to be super intentional if you want to freeze everything inside.
Which brings us to a really powerful summary from our source material. Const prevents reassignment, object.freeze prevents immutability. Now actually scratch that. That freezing is a bit of a typo in the original text. What it really means is that object.freeze prevents mutation, which grants us true immutability. Understanding this exact distinction is honestly what separates a novice programmer from a seasoned engineer. So think about it. How secure is the data in your current application? Are you actually locking the safe, or are you